If you subscribe to the channel, you'll get lots of interesting videos like this one. And if you like the video, it'll really help us out. Please comment down below for any other interesting things. That also really helps us out as well. Hi, and welcome to another edition of Basic Theory. So today we're going to start working on proofs. And I know that strikes fear into the hearts of many, but this is actually really important for being able to do any type of theory. So the way that proofs work is that you want to show that some statement is true or show that some statement is false. And there are different strategies depending on what the problem is that you're trying to prove, what the statement actually says, etc., etc. And actually, it actually kind of depends on what you know so far. So at a certain point in taking a class, you know certain things, so the style of proof might actually be different than if you knew some later stuff. So I want to do one style of proof, which is based on the quantifiers that we have done so far. So remember that the upside down A thing means for all. Oops. And the backwards E means there exists. And what we saw last time is that the quantifier is obviously important for determining what values of variable could be true, but also the domain's also important. So the domain over which the variables are defined, it may change whether the statement is true or not. So for some statements, the real number might be true, and then the integer domain might actually be false, even if the quantifiers are kept exactly the same. So let's actually look at one domain. So let's remind ourselves of Q, which is the set of rational numbers. I have no idea why it's called Q, but that's just the name that was chosen. So it's all of the fractions, essentially, so here P and Q are integers, and crucially, we have that Q is not 0 to avoid dividing by 0. There are some cases where you do want to include the infinity case where Q is 0, but we're not going to consider that here. Okay, so let's actually talk about some terms that are used in proofs. So there are several things, such as theorem, and lemma, and corollary, and these are the main ones. So if you have no idea what these mean, a theorem you can interpret as a major result. So it's some big result that you prove. A lemma is a little result. It sometimes is a helper. So if you want to prove a theorem, it might actually be too hard to prove it directly or too long of a proof. So what you sometimes do is you use several lemmas to help prove an actual theorem. And that makes proving the theorem a lot easier because you can just say, oh, look at the previous lemmas we just did and appeal to them. And then what's a corollary? So it's a something you can conclude from a theorem or lemma. Okay, so it's just something that you can actually conclude. So, for example, all even so all even numbers are integers. And the reason for that is that all even numbers live in the set Z, which is the set of integers. So a corollary is just something that you can conclude from a theorem or a lemma. And sometimes you will add an additional constraint or some little result, so it may not be completely trivial from a theorem, but yeah, that's what that means. Okay, so let's prove a little result right here. So I'm going to call it a lemma. Usually lemmas are for helping to prove a theorem, not just a standalone result, but that I'm going to use it as a standalone result here. So what is the statement here that I want to prove? I want to prove that this is true. So for any x in Q, so this is saying that x is a rational number. So remember, Q is a set of rational numbers right here. So for any rational number, we have that 2 times x is also in Q. Okay, so this is saying if you have a rational number and you multiply it by 2, the resulting thing is also a rational number. So you may think, okay, that's kind of silly, but it turns out that it's actually really important to look at each of these things individually. So what am I actually saying here? The thing that you should draw your attention to is these two words right here, for any. So this would imply that for all possible choices of rational numbers, then this statement is true down here. No matter which x you pick, as long as it's a rational number, then we know that 2 times that number is a rational number. So the way that you start here is you usually write the word proof right here. This is to signify that the proof actually is starting right here. And at the end, I'll put something to say that the proof is done. And you don't actually have to do that, but it's just helpful for the reader if they're not as experienced with reading proofs as other people might be. Okay, so this says any x in Q works. So for the proof, I can't just give a single example. So I can't say, oh, the example 1/5 is in Q, and that implies 2/5 is in Q because this number is 2 times this one. So therefore it's true. So I would love to be able to do that, but this won't work. And why is that? Because I can't just give a single example for a for all statement. For all says every single choice of a rational number works. I can't just give a single example. Now, if it said there exists, then I can give a single example. But here, this says for any, for all. So I need to be able to work this through with any choice of rational number. So what I'm going to do is I'm going to let x be a rational number. And I could have phrased this as let x be any rational number in English that way. But as long as you just let x or whatever variable you call it be just any rational number whatsoever, then assuming that the rest of the proof works, then we have accomplished the for any part right here. Okay, so here's the thing where students often or get lost or don't know what to do. So they say, okay, I've accomplished the for all here, the for any, I guess. Where do I go from here? How do I actually start the proof? So how to start the proof. Okay, and in every single one of my classes, this is the hardest part for students, being able to start a proof. So how do you actually start it? And it really depends. So in some cases it's really easy, in some cases it's not quite so straightforward. The one tried and tested approach that I take is appeal to the definitions. So in some sense, the definitions are your friends. Okay, so what is the definition here? Well, the definition of a rational number is that it's some integer over another one. That's what it means to be a rational number. So that x is equal to p over q for some integers p and q. That's what it means to be a rational number. Now, appealing to the definition doesn't always work, but it very, very, very often is the right starting point at least. Okay, well, now we just got to figure out whether 2 times x is in Q. So let's see, well, what is 2 times x? Well, 2 times x is equal to, well, 2 times this thing, 2 times p over q, because that's what it's defined to be. So it's 2 times p over q. But what does this mean? This number 2 is just 2 over 1. That it is the fraction 2 over 1. So if I multiply these out, you know from grade school that if you have 2 fractions and you multiply them, you just multiply the tops and the bottoms. So here I get 2p on top and q on the bottom. And this may seem completely trivial to you, but this is how you actually have to show a proof step by step. So what does this tell us? Well, q is an integer. I'll just say integer. Because q was defined to be an integer to start with, so it has to be an integer. But 2p is also an integer. Why is that? Well, 2 times an integer is also an integer. So this tells us right here that this thing right here is a fraction. And so, therefore, is in the set Q. Because it's the division of 2 integers, the bottom is not 0. The top could be 0, but it doesn't matter in this case because I'm multiplying by 2. So as long as it's some integer over a non-zero integer, which this is, then therefore this must be an integer, a fraction, and therefore must be a rational number. And so that tells us that 2 times x is in Q. So what I can put at the end of the proof here is QED. It's actually a Latin phrase. It means we have proven what we wanted to show. Quod erat demonstratum or something like that. But we have shown what we wanted to prove. Why? Because we let x be any rational number. Whatever rational number you're thinking of, you can plug into here and verify it for yourself. I'm not looking at any particular rational numbers. I'm just picking any one at all, and I'm just working with that rational number. And what we have shown is that the resulting number is rational. So hopefully that was interesting. Leave other problems that you want to show, you want to proof for down into the comments. And we're going to be looking at more proofs in the upcoming videos, so stay tuned for those. There are many links down in the video description if you want to support the channel, such as liking and subscribing to the channel, as well as our Patreon, our Discord server, and many other links that you can do to support us. And as always, I'll see you next time.